hopes that the Viking missions might find clear evidence of life. But the findings were not clear, as we will see in a NASA film called 19 Minutes to Earth.
It was not just another day on the planet Mars. A spacecraft had successfully landed and was monitoring this unique planet. The information was transmitted, and it took 19 minutes to reach Earth. Even from the beginning of the Viking mission to Mars, we began to assemble more than just pictures of the Martian surface. As information was received, we began to piece things together and to understand a place, a planet other than our own. As the planet was orbited, we began to understand Mars through a series of incredible photographs. Photographs that, when assembled, told of the planet's history. We found remarkable evidences of running water. Here are just a few of what appear to be dried-out riverbeds. Although other evidence states that liquid water could not flow on Mars today, we can see that at one time in the past, liquid water must have flowed on the Martian surface. When did this take place? And was there life on Mars when these channels were filled with water? We now know where part of the Martian water is today, and that is in the permanent polar cap. Previously thought to be frozen carbon dioxide, we now have evidence that the permanent polar cap is largely composed of water ice. Here you can see channels formed through melting of this ice. Other photographic evidence reveals a closer look at the Martian Grand Canyon, a system of huge canyons extending for 2,000 miles across the planet. What forces caused the surface to split apart in so many places? This raises the question as whether Mars is dynamic and active. Is it similar to Earth in that its volcanoes erupt lava on the surface? The evidence is clearly seen that Martian volcanoes have erupted in the past, and from this mission, we know that at least one quake has taken place recently on Mars. So Mars is alive, and we now have a general idea of the thickness of its crust. Further evidence of volcanic activity in the past is seen from the surface, where a variety of volcanic rocks are pitted with gas pockets and sharp or angular in appearance. These rocks face the day-to-day environment of Mars, and obviously, many have been reduced in part to the Martian dust. Let's examine the Martian environment as told to us through the Viking mission. To begin, the temperature. The temperatures appear to vary the same day to day, starting as an approximate low average temperature of 190 degrees Kelvin just before the Martian dawn. The temperatures rose to an average upper temperature of 240 degrees Kelvin. This temperature range appeared day in and day out relatively the same, almost to the point of monotony. Next, the atmosphere. The extremely thin upper Martian atmosphere consists of some familiar gases. The most abundant is carbon dioxide, a gas that we breathe out. There is carbon monoxide, dangerous to life as we know it. Argon, oxygen in small amounts, Atomic oxygen, nitric oxide, and a small but significant amount of nitrogen. Additional argon and nitrogen data reveals that Mars once had a much denser atmosphere, which could have supported running water. An analysis of the Martian soil shows an iron-rich clay with an unusually high amount of sulfur. The elements that make up this clay are familiar: iron, silicon, magnesium, aluminum, calcium, and sulfur. In terms of abundance, silicon and iron are in the largest amounts. Silicon is also one of the most abundant elements in the Earth's crust. Magnesium, aluminum, calcium, and sulfur exist in significant amounts. The soil samples appear to be very similar in composition at the two different sites on Mars, but nowhere were organic carbon compounds found in the soil. The absence of organic carbon compounds affects the interpretation of the 3 biology experiments conducted on the surface of Mars. One experiment used a sample of Martian soil moistened with a liquid that included foods that Earth microorganisms thrive on. A sample of the Martian atmosphere was pumped into the chamber, and if there were microorganisms in the soil, the gases given off would later be detected, possibly indicating the presence of life. Let's take a look at the results of this experiment. If there is life, the gases should vary over the days shown. This data does not exclude the possibility of life, but neither does it strongly support it. The second biology experiment involved another sample of Martian soil, also moistened with a liquid containing nutrients. But this time the nutrients were tagged with radioactive carbon-14. If the organisms were in the soil sample, they would have taken in the nutrients and passed off radioactive carbon with their gases. The gases, when analyzed, would have indicated the presence of life. Let's take a look at the results of this experiment. The soil samples behaved remarkably similar at both landing sites on Mars. Here is a graph of the results at one landing site, and here is the graph of the same experiment at the other landing site. The similarity is remarkable, showing a reliable experiment, and the immediate change from radioactive carbon dioxide to carbon monoxide strongly suggests the presence of life, although there are non-biologic explanations. Still, let's compare this experiment conducted on Antarctic soil to that on Martian soil. By itself, you can see this experiment could favor the presence of life. But remember the first experiment, nope organic carbon compounds, and finally our third experiment. In the third and final biology experiment, a sample of the soil was placed in a chamber where it received a small amount of moisture and an atmosphere of carbon dioxide gas tagged with radioactive carbon-14. Simulated Martian sunlight was introduced, and if plant-like organisms were present in the soil, they would capture the carbon-14. Later, the original carbon-14 gas was flushed out of the container, and the chamber was heated to over 1,000 degrees Fahrenheit. If there was carbon-14 in the soil sample, it would have been detected when released in the heating process. This would indicate plant-like organisms existing on Mars. Let's examine the results and see if life was indicated by this experiment. First, the data itself. Let's take a look at this information as shown on a graph. From this information and supporting evidences, we cannot conclusively say that life is or is not present in the Martian soil. With certainty, if life does exist on Mars, it most likely is in relatively few numbers. One final discovery in the Martian mission dealt with its moons. An extremely close flyby of Phobos has given us information that could lead to invaluable data concerning the origin and evolution of the entire solar system. Are the Martian moons captured asteroids? And are they slowly being pulled apart by the Martian gravity? While this mission has answered many questions, it has raised still others.
We do not yet have conclusive evidence on whether or not some form of life exists on Mars. Some data support the possibility that Martian life could conceivably exist. The Mars atmosphere includes all the basic materials needed for life: nitrogen, carbon, oxygen, and water vapor. Mars ice caps contain much water. Summertime daylight temperatures at the equator are about 80 degrees Fahrenheit. But there are also data that are contrary to the notion that Martian life could exist. The atmospheric pressure is only about 1% that of Earth, a pressure that would cause animal blood to boil. Water would vaporize instantly in the thin atmosphere. There is not enough ozone in the Martian atmosphere to block life-damaging radiation. Temperatures at the Mars equator fall to as low as 150 degrees below zero at night. Clearly, more study is needed to see if life exists on Mars, or if it once existed and perished there. Scientists envision an unmanned robot, a surface rover, to be sent to Mars to drive to secluded valleys to search and probe for life. This Mars rover would weigh about 220 pounds. Other proposals are to collect and return samples of Mars soil to orbiting Earth laboratories for analysis. Next time, we will take a look at Jupiter, the next planet beyond Mars in our solar system. Until then, this is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.